Welcome everyone to the study guide review video for the probability and sampling test. So this is Unit 7 test, and I'm going to give it to you on Desmos, just so we get a little practice before the MCAT of taking math tests online. You should use scratch paper, use notes, use scratch paper and pencil throughout the test to help you. Okay, problem 1, you pick a block out of this bag without looking. What's the probability of picking a block that is not a star? So looking at this, we have 1, 2, 3, 4, 5 stars, and 4 moons that are not stars, so the probability is going to be 4/9. Okay, this is just like a multiple choice question. You choose that, you move on. Alright, question 2. A principal wants to know if students want to change what is on the lunch menu. Which strategy is most likely to produce a representative sample? Okay, so the key idea here for a representative sample is we get a representative sample best if we have complete randomness. Because, I mean, it is an interesting thought in like a big picture, but when we do complete randomness, we're more likely to make sure that we're getting like all different sorts of people, and our own biases aren't coming into play. So if we select tables in the lunchroom at random and then we ask the students sitting in those tables, it's not going to be representative, or it's less likely to be, because people that all sit together at the same table might all have the same opinion. So we might have bias there accidentally. If we generate a list of all students and then we ask students randomly selected from the list, that's going to give us the most degree of randomness, and so we're going to think that it's going to be most representative. If we asked all the students who bring their own lunch to school, then again, that's going to be biased, right? Because they already don't buy the school lunch, so they're going to have stronger opinions on what to change the lunch menu to. And then if we select teachers from a list at random and have those teachers select one students, then those teachers might, choose their favorite students, right? And then there might be some bias involved in like what those students feel. Okay, so I would say the first and the fourth aren't likely to create like a ton of bias based on the question that's being asked. But the most representative sample is going to be just like kind of as random as we can get. All right, question 3. This was just the problem setup, so the actual question will be on the next slide. Ebony is curious, do people attend volleyball or basketball games? Do more people attend volleyball or basketball games? She went to a random sample of 40 games, 20 volleyball and 20 basketball. At each game, Ebony recorded the number of people. So here we have dot plots for volleyball and basketball. And we're going to use those to answer some questions. So problem 3, based on the data, select all of the true statements, select all that apply. Basketball games have a more consistent number of people than volleyball games. Okay, so if we're thinking about consistent, we're thinking about variability. So we can think about the range or the interquartile range. Here in basketball, right, this is 80 people. This is 1, 2, 3, 4. This is 40 people because we're counting by tens. 50, 60, 70, 80. Okay, so all the number of people are in that range between 40 and 80. But if we go to volleyball, we have 10 people for one volleyball game, and then we have 100 for another volleyball game. So it's this very big range. And if we found the interquartile range, the IQR, the same would be true. So basketball games have a more consistent number of people, right? The range that the data falls in is smaller, so there's less variability. Then we have volleyball games tend to get more people to attend than basketball games. Okay, so if here we're looking for the center of the data, and you could find this by finding the median, but it's probably not really necessary. Right, so it's basically like where is around the center for basketball and where is around the center for volleyball. And we can see that the basketball center is higher. So I guess I can like really briefly talk about, right, we could do this basically to find the median. And and the median is going to be 70 for basketball. And then we could do the same thing for volleyball. But I mean, it's fine if you're sort of visually doing the same process, crossing off one higher, one lower, until we're left with the median for volleyball as being 30. So volleyball games tend to get less people, not more. Basketball games tend to get more people. Volleyball games have a more consistent number of people than basketball games. That's not true. That's the opposite of the first one that we already choose. And then lastly, we have all basketball games have more people attending than volleyball games. That is not true, right? There's 2 volleyball games where we had 100 people, and the maximum for the basketball is 80 people. So we have more, again, variability for the volleyball game. It's more spread out. It depends more. So it's not always true that basketball games have more people. It's just like more often the case. Cool. All right, question 4. 6 friends use a spinner with 6 equal sections to decide who will vacuum the floor of their shared apartment. Abdel says, after 6 weeks, I will have vacuumed exactly 10 times. Do we agree with this statement? Okay, so for Abdel, we have 6 sections, and we have that he's going to get chosen 1/6 of the time. Okay, so what we could do is we could do 1/6, and then we multiply by the 60 weeks, and we are going to get 10 times. Okay, however, I still disagree with this statement because we have that Abdel says, after 60 weeks, I will have vacuumed exactly 10 times. The exactly is the issue here. Okay, we're not sure it's going to be exactly 10. This is probability. So 10 is the best guess that we could give. But anytime we're in the realm of probability and we see something like exactly, we're sure, anything like that, we should be alarmed. Probability is really just our best estimate. So that's why we're going to disagree with this statement. Okay, something like this. I disagree with Abdel because of his use of the word exactly. Well, 10 times out of 60 is the best estimate we can give for the number of times you will need to do the dishes. This is probability. There's chance involved. We can't be sure it will be exactly 10 times. Cool. Okay, maybe you don't have to write as much as I did, but you still definitely would need to explain in order to get full credit. All right. Question 5.1. The Spin and Dine restaurant sells bagels. You spin 2 spinners to select one random type of bagel and one random spread. How many different possible combinations could you spin? Okay, here is a good opportunity for you to write stuff down on a piece of scratch paper. So I'm just going to pull up here because I also did the paper version of this. And I am going to create, and this is what you want to create to answer this question, right? Like a probability tree or some other way of representing all the different combinations, right? So we can get a plain or a poppy seed bagel, and then we can get plain with butter, plain with cream cheese, plain with peanut butter, plain with jelly, poppy seed butter, cream cheese, peanut butter, jelly. So there's 8 possible different combinations. Okay, so once we draw that out, it gets a lot easier, and there's not necessarily room to do that on Desmos. I mean, you could kind of write right over it, like that'd be fine. But drawing it out on paper is a good idea. Just like when you're taking the MCAS, you want to make sure you're taking time using your scratch paper. Okay, then based on this 5.2, what's the probability of spinning a poppy seed bagel with either butter or cream cheese? Okay, so again, going back to my scratch work here, we want poppy seed with butter. Oops. We want poppy seed with butter or poppy seed with cream cheese. So those are 2 of the 8 combinations. So the probability of spinning poppy seed bagel with either butter or cream cheese is going to be 2/8, which simplifies to 1/5, or 25%, or 0.25. Okay, so we take the 8 possible combinations, and these are 2 of the 8 possible combinations. Great. All right, problem 6.1. Darius thinks school should start later and wants to know if others agree. He surveys a random sample of 40 students and finds that 26 of them agree. First question is, what's the population for Darius's question? Okay, the population is the big group that we're studying. Okay, so he is trying to figure out, who does he care about? Who is he asking? And he's asking students at his school. So the population is all students at his school. That's not 40 students, right? It's probably much more than that. All the students at his school. It's not 26 students. This is the big group, and then we sample from that. Okay. So then we get to problem 6.2. Same setup. If the school has 240 students, how many do you predict will agree? Okay, so in terms of the work for this, we took a random sample and we found that 26 out of 40 agreed. So that's going to be 65% of students agree. Okay, if there are 240 students, then we want to find 65% of 240, right? So to do that, right, on our calculator, we can find 65%, or 0.65, times 240, and we're going to get 156. So we predict that 156 students will agree by using the probability that we got, the proportion we got, 26 out of 40, from the random sample, and then applying that like proportional reasoning to say, okay, so based on the sample now we can make this prediction about the whole population. Okay, it probably won't be exactly 156, but that's our best mathematical approximation, right? And it should be close to that, or it's our best guess that it's going to be close to that. Cool. And then problem 6.3. So same setup again. The next day, Darius surveys another 10 random students and finds that 6 of them agree. Does this make you more or less confident in your prediction? Okay, so we have 6 out of 10. Oops, 6 out of 10, which is going to be 60%. So we did another sample, and we found that 60% of students agreed. In the last sample, we had 65%. So even though those aren't the exact same number, we have to think about the fact that if we only interviewed 10 students, the closest we can get to 65% is 6 of them agreeing or 7 of them agreeing, but there's no way to get 6.5 students to agree, which is the only way we get 65%. So we're going to be more confident in our prediction because the probability, or like the ratio or proportion of students that said they agreed, was still close to this 65%. So I'll write that out. Okay, so we can say something like this. 6 out of 10 students agreeing this sample is 60% of the sample. This is as close as we can get to the 65% that we got in the last sample, given the sample size of 10. Thus, I feel more confident that about 156, or in the 150 to 160 range, right, because these are just estimates, of students will agree. Okay, but if we got like 2 out of 10 agreeing and we had 20%, that'd be very different than 65%, and then we should feel less confident. But if it's about a similar percentage or probability, we should feel more confident. All right, and now we have problem 7 set up, and then we'll get to the questions in a moment. Alina is wondering if her class has a longer commute time than her friend Dylan's class. Alina selects a random sample of 9 students from each class and asks those students how long they spent commuting to school yesterday. So we have 2 sets of data here. We have Alina's and we have Dylan's. Okay, 2 different samples. Yasmin looks at the data and says that each class has 9 students. Is she correct? Okay, no, she's not correct. We asked 9 students in both of them. They tell us that we've randomly selected 9 students from each class, but that doesn't mean those are the populations of the class. That means those are the sample sizes. So Alina sampled 9 students per class, but the actual populations of those classes could and likely are bigger. Cool. And last but not least, in which class do students spend more time commuting? Alina's class, Dylan's class are about the same. So if we look at Alina's class, we can identify the median very easily, right? Our median here is 30 minutes. And then if we go to Dylan's class, we can also find the median by trying to find the middle, right? That's what the median means. And we get 20. So in which class do students spend more time commuting? That's going to be Alina's. Alina class spends, Alina's class is a median of 30 minutes of commuting time, while Dylan's has a median 20 minutes. Okay, it also says use at least 2 different pieces of evidence to support your claim. Depending on the definition, I think they might kind of also wanting us to comment on the interquartile range. And since we've learned how to do that, let's just take a step to review that. So here, Q1 is 25, quartile 1, and Q3 is 40, so we have an IQR of 15. So 50%, the middle 50% of the data is falling within 15 minutes of our 30-minute median. And then we can do the same thing here. We got that our median was 20. So then we kind of split this down the middle. And the IQR here is going to be, the first quartile is going to be 15. And then the third quartile is going to be 25. So our IQR is 10. So Dylan's data is like a little bit closer together. There's less variability. But they have like kind of pretty similar 10 minutes, 15 minutes. The only way that the IQR would really like go against the median here is if the medians were really close to each other, like within 1 or 2 points. But say Dylan's IQR was like 30 and Alina's IQR was like 4, then we might make a different decision because Dylan's data might be like really spread out and more variable so that it was like hard to tell, and Alina's would be like we have more confidence because the data is really close together. But I'm just going to add like since the interquartile ranges are similar, we can trust the medians. To give us the necessary information. Okay, and that's it. So the actual test is going to be on Desmos. It's going to be exactly like this. Exactly like this. Right, the study guide I gave you. I'm also going to post the paper version of the answer key. It's the exact same questions, the exact same answers, just so you have a paper version. But when you actually take it in class on Friday, it'll be on Desmos. All right, good job, everyone.